Nothing beats. In this video, what we're going to do is we are going to investigate a function's concavity and also use the second derivative of a function to help us find local extrema. And also, how does the second derivative of a function relate to concavity? Well, let's find out. Concavity. Well, what we're going to do is we're going to start by assuming we have a function y is equal to f of x. And let's assume that this function is twice differentiable. In other words, meaning we can differentiate it twice and its second derivative exists. So we got a function, its second derivative exists. Then, of course, things that we want to just refresh here, the derivative of the function, as is the main topic of a Calculus 1 discussion, say dy dx is f prime of x, that is the function that gives us the instantaneous rate of change of the function at x. However, if I then differentiate that function again and get the second derivative here, d squared y over dx squared, or in other words, differentiate the derivative dy dx with respect to x, giving us f double prime of x, that second derivative of the function, well, now that's giving us the instantaneous rate of change of the derivative, right? It measures how the derivative changes. And like I said, this second derivative gives us information about how the derivative changes. Now I want to take a look at a couple pictures here. This one first. Here is just some function. Looks like a parabola of some sort. And this function, what we have given to us on the screen is the function, obviously. That's the blue function. And we have a point over here, right? There's some point on this function and the corresponding tangent line associated with that point. Also, right here is our actual numerical value of the derivative of this function at that corresponding point. And so we can see where it's at right now. It's a negative slope. Slope of the tangent line at that point is negative, approximately negative 2.63. And what we want to do is look at as I increase my x. So I'm going to move this slider up here. And as we move the x in the left to right direction, what happens with the slopes? Well, we can see they're still negative over here, right? But as we move along, the slopes are getting less and less negative. And eventually, we're going to get to a place where it's actually zero slope. And after that, we have positive slope. And in fact, the slopes get bigger and bigger and bigger. And what this diagram is supposed to be showing us here is that this shape, this curve here, as I move from left to right, the slopes are actually increasing in value. And of course, we were just talking about that, right? The second derivative tells us how the slope change. And so if a function has a slope which is increasing, like in this graph right here, then our second derivative must be positive because it measures the rate of change of the derivative. And notice that this function indeed is a concave up function. Let's look at the concave down situation. Same kind of idea. Got my concave down parabola here with a point on the graph and a tangent line with the corresponding numerical value of the slope of the tangent line at this point. Right now we're at this point right there. Slope needs to be positive, approximately 3.02. And now, as I move in the x direction, notice that my slopes are decreasing, right? Really positive down there. And as I move to the right, they're still positive, but they get less and less positive. They're getting smaller. They're decreasing. And eventually they get to a point, again, where the slope is zero, somewhere at the vertex right up here, right? And as I continue to move to the right, they get negative, and eventually they get more and more negative. And so this diagram is supposed to help us visualize, oh, we have this shape of a curve, which is a concave down shape. And the slopes themselves are decreasing in value from really positive over here to less positive, eventually 0 to negative to really, really negative. The slopes are decreasing. The second derivative measures how the slopes change. And hence, if the slopes are decreasing, the second derivative should be negative. And that's what we're supposed to take away from this. So you go back here, right? We're investigating the second derivative and how that information about how the slope changes in the graph. So, what does this second derivative of a function really tell us about the graph of the function, especially based on that inspection that we just saw? A couple things. First of all, assume that you have that f double prime exists. Okay, you got a function, its second derivative exists on some open interval, let's call it I. Then, if the second derivative is positive on this interval I, that must mean that the derivative f prime of x is increasing, and just like we saw in that first diagram, the function must be concave up on that interval for this to happen. The slopes are increasing. Whereas, if the second derivative is negative onto interval I, then that would mean that the derivative function, f prime of x, is a decreasing function on that interval I. And that would also mean that the function is concave down. So basically, concave up, second derivative here is positive, concave down, second derivative is negative. And that's the big takeaways thus far in this video. Now, what happens if your second derivative is 0? Because that can happen. We didn't look at that yet. If the second derivative is 0, then its derivative should be constant, right? Because derivatives of constants are 0, and the second derivative is the derivative of the derivative. And if the first derivative is constant, then the function must be linear because its slope never changes. So you just have a line. And when you have a line, the second derivative is equal to 0 since it does not have any curviness to it, if you will. It's linear, the slope is constant, and the slope never changes. Therefore, its second derivative is 0. Now, there are points of interest in which we're interested in, in which a function can change concavity. And when we say that a function changes concavity, we mean concave up to concave down, or vice versa, concave down to concave up. When that happens, we call that point a point of inflection, or simply an inflection point. So how can that look? Well, here's one such example of a function. We notice that right about right there, whatever that is, right? Let's just call that location C for the fun of it. Then for x values less than c, notice that the second derivative here must be negative. Now, why is that? Because along this part, right, we're concave down. And to the right of x is c, x is larger than c, the second derivative must be positive because the function is concave up, like we just established. And so in this case, the function changes from concave down to concave up at the location of x is equal to c, and notice that the second derivative changes signs from negative to positive at this location. For this reason, we would call this an inflection point, or just a point of inflection, if you will, whatever you prefer. So you change from concave down to up, something happens like so. Now, that's not the only way it can happen, but that's just an example. How about this graph right here? Something similar, but kind of the other way around. Right around there, let's call that location again x is c. Well, then notice for values of x less than c, the second derivative of this function must be positive. Why? Because for values of x less than c, the function is concave up. For values of x larger than c, the second derivative of this function is going to be negative, because right over here, concave down to the right of x is c. And again, we see that the second derivative changes signs at the location of x is c, in this case from positive to negative, and we would still call this an inflection point because the second derivative changes signs at that location. So it's all about changing from up to down or down to up in terms of concavity, and when that happens, we call that point a point of inflection or an inflection point. Let's look at an example depicting this exact idea. Here is a polynomial function, f of x, which is negative x to the fourth minus 2x cubed plus 12x squared. Our goal is to figure out all the intervals for which the function is concave up, and also the function is concave down, and then also identify any inflection points if there happen to be any. So in order to do this, like we were just talking about, we are going to find the second derivative, figure out when that's positive and when that's negative, and then see if there's any sign changes at these locations for which the function changes concavity, if that's the case. Let's see. All right, well, first derivative here, f prime of x, it's going to be a negative 4x cubed minus a 6x squared plus a 24x. Now we need the second derivative as well. So the second derivative, f double prime of x, negative 12x squared minus 12x plus a 24. Now, notice, factor out a negative 12. We're left with an x squared plus an x minus a 2, which of course can be rewritten as negative 12 times x plus 2 times an x minus 1. And so notice that this second derivative is never undefined. However, it is equal to 0 if x is equal to negative 2 or if x is equal to 1. And so just like we did when we looked at the sign analysis for the first derivative, trying to determine where a function was increasing or decreasing and where these local extrema might be, we play a similar game here for concavity. Can we find really the critical points of the derivative function? And in that case, we look at if there's sign changes in its derivative, which is the second derivative, and when that happens, we could have an inflection point there. So in this case, the possible points of inflection are first going to be at x is negative 2 and at x is 1. Let's draw in some sign charts here. These are the values of f double prime, and these are x's down here. And we got our f double prime right above. Let's use that form of f double prime. If I plug in, say, a gigantically negative number, then we have a negative times a negative times a negative, negative to the left of negative 2. At 0, the second derivative is positive, so positive between negative 2 and 1. And at a gigantically large positive number, negative times positive, it's negative. So this sign chart here for f double prime tells us several things. One, first thing, f double prime of x is positive for values of x between negative 2 and 1. And therefore, because that's true, it must mean that f of x is concave up for values of x between negative 2 and 1. Moreover, the second derivative of this function is negative for values of x from negative infinity up to negative 2, and it's also negative, the second derivative, for values of x from 1 to infinity. And therefore, a similar conclusion can be made, is that the function itself is concave down, in this case, for values of x in this interval, negative infinity to negative 2, union 1 to infinity. So we accomplished part of it thus far, right? We found the intervals for which the function is concave up and concave down. However, we'd also like to identify any inflection points, and we can see, in fact, that at the locations of x is equal to negative 2 and x is equal to 1, this function's second derivative changes signs from either negative to positive or positive to negative. And for that reason, we have that the function itself has inflection points at the locations of x is equal to negative 2 and also at x is equal to 1, because we see in the sign chart right there, its second derivative is changing signs. So we can see how the second derivative now helps us get more information about the shape of a curve, right? Embeds a lot of important information about it. Now, that's not it, because now we'd like to relate local extrema with the second derivative. Another way of using the second derivative to help us, and this is what brings up what is referred to as the second derivative test. So that just means we're using the actual second derivative to look for local extrema. Now, how so? Well, let's first start by assuming that this value of x is equal to x is equal to c, be a type 1 critical point. So remember, what that means is that the derivative at this function at c is equal to 0, and it also means, right, that c is in the domain of the function. We're also going to assume the function is continuous on some interval, in particular an open interval, containing the point c. So all we're saying is we got a type 1 critical point. The function is nice and smooth at this location, and its slope is 0, and nearby we're also continuous. Then, assuming that's all the case, the claim is if f double prime, the second derivative of the function at this location c, is positive, then the function must have a local minimum value at this location, x is equal to c. Now, why is that? Because, well, let's take a look at this picture and kind of think about it. If we're continuous nearby at x is c, say right over here and right over here, then if we're continuous and at that location we have that the derivative is 0 at x is equal to c, right? Because we're assuming it's a critical point of type 1. And moreover, the second derivative is positive there, then we must be concave up. And an only way that can happen is in a picture like this, in which we have a local minimum in a smooth function. So that's part of the second derivative test. The other part, you kind of may think, well, switch it around, do the other way, right? Now, if the second derivative at this type 1 critical point is negative, then the function is claimed to have a local maximum at this location of x is equal to c. And so, again, you look at this picture, we must have a continuous function at least nearby to x is equal to c, so to the left and to the right of it. And at c, the derivative must be 0 by assumption, so slope is 0. And then if the second derivative at this location is negative, then the function must be concave down. And the only way that that's going to happen is if you have a picture like this, in which we have a local maximum point at x is equal to c. If it ends up that the second derivative at this location is 0, then we don't get anything. We don't get any information. We say the test is inconclusive, and we don't know what's going on there. The function may or may not have a local extreme point at the location of x is equal to c. And so the only way to really go figure that out under this circumstance is to go and use the first derivative test to conclude something. So the second derivative test is a little bit limited in the sense that we must only be dealing with the smooth types of situations in which the derivative of a function is 0. And moreover, if we go and check the signs of the second derivative, well, if it's positive or negative, we can conclude we have either a local minimum or a local maximum point. But if the second derivative is 0 there, then we gotta go do the other test. So it's very specific in the sense that we gotta be dealing with that exact circumstance. However, it does work. Here is an example. Consider this polynomial function. F of x is equal to 2x cubed minus 9x squared plus 12x plus 1. Part A, we're going to use our second derivative test that we just discussed to find all the local extrema of the function, assuming it's possible. Now again, it's a polynomial function, so I know its derivative is never undefined, and the critical points are always going to be type 1 critical points. Let's go and find those critical points. F prime of x is going to be needed to do that. So differentiate that function. 6x squared minus 18x plus 12, which can be rewritten as 6 times x squared minus 3x plus 2. In factoring further, 6 times x minus 2 times x minus 1. So we can see that this function's derivative is equal to 0 if x is equal to 2 or x is equal to 1. And these are our critical points, and of course, they are both type 1 critical points. So that criteria is satisfied. Moreover, this function is continuous for all real numbers x, so it's going to be continuous close by to these critical points as well, and the second derivative test is applicable. And so to do the second derivative test, we must find the second derivative. Second derivative of this function is 12x minus an 18. And now all we do is we plug in our values into the second derivative. F double prime of 1 here. Well, that's 12 minus 18. That's a negative 6. More importantly, it's negative. And because it's negative, that means the function itself is concave down at that location, and thus at x is equal to negative 6, f has a local max point. So what does it look like there? Nearby? It's got to look something like that, right? If I plug in x is equal to 2 in my second derivative, then 2 times 12, 24 minus 18 is actually a positive 6. And more importantly, it's positive. Don't think they're always going to be opposites like this, like just a coincidence. Because the second derivative is positive, then it tells us that at x equals 6, f has a local min point. Because the function must be concave up there, and it's got to look something like that nearby. And so there's one example of using the second derivative test to determine some local extrema of a function, in particular, especially polynomial functions that are nice and smooth. This test can come in quite handy sometimes. Now, the second part of this problem says, let's go ahead and find also, while we're at it, all intervals for which the function f is concave up, and also where it's concave down, and also identify any inflection points. So let's go ahead and do that. In order to do that, we must actually go and do the sign analysis on the second derivative. And notice, right up here, whoop, there's our second derivative function. And f double prime of x, which is equal to 12x minus 18, that's going to be equal to 0 if x is 18 over 12, or equivalently 3 over 2. And thus, this is the location that has the potential for which the second derivative may change signs. So let's go do the sign analysis down here. Here's our f double prime. Here's our x. Here's the location of 3/2 for x. We know our second derivative is 0 there. Plug in a giant negative number. We're going to get a negative number. Plug in a giant positive number. Positive number. And therefore, we can conclude that f of x, couple things, right? F of x is going to be concave up if x belongs to the open interval 3/2 to infinity, because that's where its second derivative is positive. The function is also said to be concave down if x belongs to the interval negative infinity to 3/2, since that's where the function's second derivative is negative. And then finally, because the second derivative changes from negative to positive at this location, it also follows that the function f of x has an inflection point or point of inflection at the location of x is equal to 3/2. And there you have it. So this video is supposed to connect several ideas, right? First of all, what does the second derivative of a function tell us about the shape of the graph of the function? If the function's concave up, second derivative is positive. If the function is concave down, the second derivative is negative. If the function is linear, the second derivative is 0. And, moreover, if you have the nice situation in which you have a critical point of type 1, and we're continuous nearby this point, simply evaluating the sign of the second derivative can classify that point as either a local max or a min. And we did several examples to help us understand this. So hopefully that video helps with the idea. And from here, we're going to piece together all the things we've talked about so far in terms of derivatives and what they tell us about graphs. And we're going to go do some amazing graphs. Until that next one, you know it, it's Math and Beats, and I'm out.